Hello, everyone. This is the first of our contributor spotlight series where we're going to talk to Unison contributors and do a little coding exercise. And I figure why not dog food with one of our own first. So here we have Fabio, and today we're going to talk to him about the concurrency library, which I'm super excited about because it's not every day that I get to talk to Fabio about concurrency. So we're going to get started. The plan today is ask some kind of broad questions about concurrency, about the library, get a sense of the API, and situate it within the context of all of the stuff that's happening in Unison. And then we'll do like a little kind of simple coding exercise together. And if folks have questions, feel free to drop them in the chat and I'll read them out so folks can follow along if they're just listening. Yeah, with that, we'll get started. So thank you so much, Fabio, for joining me today.
Thank
How are
you.
you doing?
Thank you. I'm doing great. And I also want to tell people quickly that I'm going to do office hours straight after. So if you want to, sort of chat to me about any of the stuff that we're going to talk about today or anything else, yeah, just drop by. Uh,
Yeah,
so yeah,
awesome.
let's go. I'm excited for this.
Okay, yeah. So starting pretty broad, I
Yeah.
know you are one of the experts in this domain. I'm curious how you got into the field of both distributed and concurrent computing. Like, what drove you to focus on that, and what's your background in that space from?
Yeah, that's an interesting question. So in terms how I got to expertise, it's a mixture of I've been lucky to engineer a distributed system essentially from the first role in my career up to way till now, kind of working on greenfield, high scale stuff. So it was that plus reading a lot of papers and sort of like, yeah, kind of the academic side. Um, in terms of why I was drawn to it, I'm not too sure. I just liked it. Like with concurrency, I think like I got it sort of straight away, the mindset. But but then distributed system felt sort of very academic and hard to get into. And then actually, when I learned functional programming, which is totally unrelated, I started reading papers for that, which are a lot more accessible than like distributed system papers. And even yeah, no, it sounds weird, but yeah, there's like things like functional pairs and papers that are like directed at like non-practitioners, whereas with distributed system is very much like,
You have to
practitioners
be a
writing for
distributed
practitioners.
systems nerd
Yeah,
to
yeah.
get it.
But
Gotcha.
then the functional programming thing kind of told me, hey, with papers you can learn a lot better, in my opinion, than books. They're more up to date. There's less debate. And then I was in a position where, okay, I know concurrency fairly well. I'm working on distributed systems, and I'm not scared to read papers anymore. And so that triggered like kind of nice growth in terms of, you learn more, you apply it in practice, see what works, what doesn't work, read more stuff, and so that's how I got to yeah to today.
Yeah,
It's not
this
as
is
scary as it sounds, like it sounds scary at first, but before you know it, you're a practitioner after a few
huh. There's hope
attempts.
for all of us.
Yeah,
You've given some interesting tips about reading some of the distributed systems and concurrency papers in previous streams, and I'm just curious. Could you reiterate, like, as a non, let's say, a non-expert, uh,
yeah,
but working practitioner, what are some of the things that you would recommend as you're approaching these papers?
yeah. So this applies to papers in kind of all of the fields that I've read papers to. So I don't know about non-computer science, but at least for like, distributed system, programming languages, concurrency, database design. Um, well, first tip, don't be scared. Uh, Second tip, don't be scared to drop out of a paper, so to speak. Like at first I thought, oh, if I don't understand every page of this, essentially I'm not doing anything useful. Instead, like read some. When you stop understanding it, drop it, and maybe you'll pick it up a few months later. You do that a few times, you realize, oh, I actually know what they're talking about now. And then there's like slightly more, practical tips. Like, if you don't feel like going through the proof side of a paper, don't do it. After a while, you learn. There's like schools, and like when there's a researcher which has a certain set of opinions, and then papers done from sort of by his PhD student or her PhD students will sort of echo similar opinions, and so you start to learn, kind of. Like trends, and it's like, oh, is this these people? So I kind of know what they're going for. Um, and then the other tip that I quite like is when you want to first understand an idea, don't read the paper that introduced it. Read later papers that would summarize it in simple terms in the previous work section. And then you only read the original paper once you kind of understand sort of what's going on with that idea. So if you want to read on about Paxos, just start from the part-time parliament, which is the paper that introduced it, but pick any other paper, like something that's called Revisited, or anything that sort of came after it, and you get a nice a nice summary of that idea.
Right.
And, just in general, like, don't think that there's, like, the elected class of geniuses that read papers, and then, the hoi polloi that can't is just a smaller book. There's nothing special about it. Like any book, you need to learn a bit about the language, but it's doable. And I do think it's hard to pinpoint like what made you sort of good at something, but this, like, reading papers was amazing for me. Obviously, you have to be able to put them in practice, otherwise it's easy to get carried on with ideas that don't actually work. But yeah,
Right. No, that
so
makes
yeah,
sense. Thank you for that. That gives I'm sure a lot of us mortals hope for
yeah,
for our
yeah.
learning.
We can in the office hours, if people are interested about specific papers and stuff, we can go more in depth on that topic. But yeah, I
Awesome.
think I think that's a good starting point.
Yeah, awesome. Well, so concurrency is notoriously challenging for a lot of programmers, and I'm curious if you had to categorize some of the difficulty
Yeah.
of working in highly concurrent systems. Like, are there kind of broad domains that make it, more complex? And what
Yes.
are those kind of divisions?
So I think many people have heard of, the technical problems that can happen, like race conditions where a piece of state is modified while something else is reading it or also modifying it, and then it gets corrupted or deadlocked. But those don't really, like, describe the human, like, why is it difficult for humans to work with this. So I want to give you a couple of things that happen that are hard for most people to deal with, that you have to sort of train yourself. One would be that failures tend to be non-deterministic. So it's something that behaves correctly most of the time and then doesn't behave like you expect it to be. And actually reproducing that failure can be challenging. And there's a couple of techniques that I use when writing tests for concurrent stuff that can help, like, tests that run multiple times or simulation testing. And the most extreme case of this problem is what is sort of affectionately called Heisenberg. Uh, Kind of referencing the Heisenberg principle, where if you observe something, you change your state. It's basically a bug where it's something weird is happening, and when you instrument some print lines to see what's going on, it stops happening, and so that can be really challenging to debug. And the other thing, which is maybe at the heart of it, why it is complicated as a human, is I think as programmers we not used to loose models of execution. So if I say x is 0 and then x equals x plus 1, okay, what's x? Well, that's clearly 1 and there's no other answer. But then if x plus 1 is happening in another thread, then x in the first thread might be 1 or might be 0. And it's hard to sort of keep state space or possibilities in mind. And so if I can sort of add a tip, I think what what you need to develop is the ability to see interleavings. So an interleaving is a specific actual execution. So there are many, like there are several orders in which things might have happened. An interleaving is one of those orders. You have to be able to visualize them and think almost with an adversarial mindset. So when you program normally, you're generally thinking about the right, like the happy path 80% of the time. It's like, okay, it's going to sort of do this and that. And then it's like, okay, 20%, let me think about some errors. Uh, with the concurrent algorithm, it's very easy to convince yourself that it works because your mindset about the happy path has sort of blinded you to all the other interleavings. So instead, you have to think, okay, let me try and find one where it doesn't work. I'm going to
Mm.
assume that it's broken, and let me think about how is it broken. Which kind of makes you a bit cynical. So you have to temper it if you're talking to another programmer about not the concurrency problem.
Uh-huh.
But so that's the thing. You have to assume it's broken and try and find how is it broken. And I think that helped me deal with the complexity. Uh,
Huh.
but then I want to reiterate, like most other things, it's not like intrinsic intelligence. It's like a thing that you have to get used to and practice, and then you get better at it.
Hmm.
If you care about it, obviously. Some people don't care. But so yeah, I think it's the loose mental model, like the loose guarantees. And then when you moved on to distribution, it's that squared. So if you're interested in distributed systems, I would definitely recommend getting good at concurrency fast because they're sort of like distribution light. And then once you're like confident with that, then there's even fewer guarantees when you move to distributed systems. And so you have to think with even looser mental model of what sequence of action is. Um,
Right.
so
Right.
yeah.
Do you find that the tooling has gotten better over time with helping people understand and debug concurrent programs, whether it be through visualization or testing harnesses or anything, or is it still kind of like just sitting and thinking through the processes, debugging, print lining, is it still fairly
Yes,
manual?
yes and no. So TLA plus I like to use for the this design side of a distributed algorithm, and that kind of helps you think and debug a model. But it's not very beginner friendly. You probably don't want to start your journey into the area by learning about TLA plus. Even though I do think it's simple. It's not easy, but it's a very simple idea.
Mm,
In terms of tooling, I don't know. It's very language dependent, and also the way you structure code tends to be different. So I would say, meaning like when you know that you're working on concurrency, you think about deterministic testing or how to debug complicated state early, which you don't tend to do when you write kind of normal quote unquote code. So no, I would say it's a lot of like thinking about things, adding some print lines, and then obviously there's a range of techniques to how you design things in the first place. But yeah, I don't think that there's like cross-language amazing tooling that can sort of fix this issue for you. Obviously, some language do some things that are helpful, like Go has got a deadlock detector. Some things you can avoid in Rust, but you know, it's mostly about not making concurrency a problem by accident. When you actually have to develop a concurrent algorithm, it's still like yeah, your brain, paper, and PLA plus sometimes. Uh,
mm,
at least for me, maybe other people have got a better tooling
mm.
recommendations.
Right. Yeah. So, let's dig into the design of the concurrency library itself.
Yeah.
Um, so why create this particular library? What are the problems that you imagine it solving for users, and how do you imagine people coming and using this library?
Yeah, so there's a very easy answer. That was actually created to solve a specific problem, set of problems in our own infrastructure. So the
Mm,
thing with Unison, that Unison Cloud is actually built with Unison. Uh, so there's a specific system inside it, which is sort of the core of our compute fabric that needed some concurrency stuff. And so I created the library to serve those. There's some more backstory there, which is not that interesting. Um, but the interesting thing about the library is that two things, there's four types in the library: signal, concurrent map, log buffer, and semi-space cache. So two of them, signal and concurrent map, they're very general purpose. So I do encourage people to get into using them. They can be very helpful for a bunch of problems. Whereas the other two, the log buffer and semi-space cache, they're still kind of fairly general, but they were more like, oh, we actually need these two uh, in there. So we're going to package them all together. So it's not so much a grand conceptual plan as much as it is, solving an actual problem. So we wrote a library to do it.
huh. Okay. So you have to answer the immortal question. What is semi-space cache? We'll get into like the important primitives, but just
Yeah,
at a high level.
yeah. So it's a cache, and it's nice because it's pretty simple and it's got nice properties in that there's no kind of contention when there's a cache hit. Contention means sort of multiple threads getting in each other way and slowing things down.
Hmm.
And the reason it's called Semispace is because it does, imagine like two copies of the same thing and you swap them. So that's the basic idea. Like you fill this cache, and then there's two spaces, like a old space and a new space. And then as you stop using things, they kind of move to the old space. And then when you want to evict, instead of evicting an item at a time, you make the new space the old space and you discard the old space. So it's like
Mm,
imagine like like a two-tier system where things move from one tier to another, and then the older tier just goes to trash, and the new tier become the old tier, and there's a new tier, basically. Uh, it's
Ah,
actually easier to like when you use it. There's nothing that you have to know really about this. Yeah, so Paul is linked some docs, which
okay.
I think I wrote, and I made a better job of writing in this explanation because they feel more, they make more sense. But yeah, like they just got a fancy name, Semispace, meaning space divided in half. But when you use it, it's just like you put things there and then you say collect, like evict. There's no, it's not very hard to use. That's
Gotcha.
what we meant.
Okay. Gotcha. Well, I wanted to make sure people were aware of it and also not afraid of it because of its name. So that's a
Yeah,
great overview. Thank you.
yeah,
Cool. Well, let's talk about Signal and Concurrent Map,
yeah.
and what they do for folks. So, like high level, what is Signal? What is Concurrent Map? How do folks use them?
Yeah, so concurrent map is the simplest of the two. It's basically when you have a map and you have some computations that you want to do on the keys, on each individual key. Like you want to modify a key, or you want to, um, yeah, Paul is suggesting maybe we can have a look at
Yeah,
share these types. Like, I think it's easier if you do it.
I will share. Okay. So this is the map type in Concurrent. If
Yeah,
folks can see that.
so you can create one, and yeah, you need to make it a bit bigger as well. Or you can look things inside it. But the core of the method, the core of the functionality is this alter method, where it's basically saying do some modifications on the key, and those modifications are pure, but like depending on whether the value is there or not, you might want to create a new value or change an existing value, or delete one. So imagine like this map might contain scores for players, and you want to give an individual player, increase their score, initialize their score to zero if it's not there, or if they kind of leave our server or whatever, remove the score from there. So concurrent map lets you do that by just writing a function that operates on a single key and not worry about the actual concurrency stuff that has to happen for that map to be consistent, where multiple threads are accessing, and either because they serving multiple players or because the same players got some computation happening in multiple threads. Um, so yeah, it's pretty simple. That's the one function you have to learn how to use, and there's a few helpers. Signal is a bit more interesting.
Mm,
Signal is again, there's sort of mostly a single function that does most of the work, that change function. Um, so a signal is a type parameter s, which is the type of its state. So normally, it would be some enum or struct in there, an ADT, describing what you want to do with the signal. And then you write computations on the state in the changes ability, which is sort of like a little transactional ability. If for folks that have used the state thing in the cloud, which coincidentally I also wrote, is similar to that. You can read and write into the state of this signal. But the special source is like retry, where basically like retry is gonna block your thread until the state changes. So we're gonna use this in the example, so that there's no need for now to go into a lot of detail. But basically, whenever you want to do a pure computation that modifies the state and also waits for some things to happen to that state, uh, you can use signal and signal dot changes. The one thing, the limitation of signal is that the state is monolithic, so you cannot combine multiple signals and have things operate transactionally. That signal is like all the state that you're operating on is in that one signal. Um,
mm,
but you'll see that that's still like pretty useful. I like this because the ratio to like simplicity to usefulness is pretty high. It's pretty useful given how simple the implementation is. Uh,
gotcha, gotcha. So I was looking at Signal a little bit earlier because you had mentioned it, and it uses some concurrency primitives from Base, the
yes.
library, the standard lib. And so I'm curious if you could help us understand what these abstractions do compared to, say, some of the functions and abstractions that are in io.concurrent in our standard lib.
Yeah. So there's two. Like obviously, I'm not going to talk about fork and the basic
Mm,
things to spawn trades. But in terms of state manipulation, there's two abstractions in base, uh, which are sort of introduced. as a designer of Cat's Effect in Scala, and I found it like quite a useful scheme, and so I ported it to Unison. And one is ref, and one is promise. The other one is promise.
Mm.
And each one is like the simplest way you could represent what I think are the two fundamental concepts in concurrency when you're dealing with state. Concept number one is state modification. So you have a mutable thing, you want to change it in a way that is concurrency safe when multiple threads are trying. That's one thing, one concept, and that's ref for you. The other big concept is synchronization. So, oh, I want to wait and block for a condition until that condition is fulfilled. Okay, so these are the two, the two big areas. And traditionally you would have like a lock and a condition variable to represent them. So ref and promise are similar to that. They're just sort of very simple. So what ref lets you do is modify some mutable piece of state without any effects. So you know that the modification is going to be concurrency safe, meaning if I do read and then write +1 to an integer, and so do you from another thread, we are sure that both modifications will happen. Whereas if we didn't apply any state management to that concurrent problem, we might get 0 or 1 or 2, depending on how the interleavings happen. Well, we might not get 0, but we'll get either 1 or 2, depending if we sort of did things the lucky way or the unlucky way in terms of interleavings. So that's ref, essentially thread safe mutable variable. And then promise is a thing that starts empty, and then when you kind of try and read an empty promise, you will block, and then you can write to the promise, and it will unblock every thread that was waiting on that promise. And the reason that it's simple is that this can only happen once. So a promise is a write once. It starts empty, it gets full, and then it's full. It cannot go back to empty. So you only block in one direction. And this seems like an awfully limited set of things, but when you start putting promises inside refs, you can basically build all sorts of things. You can build like mutexes or STM, like whatever you want, or signal, for example. But you do that in a way that is pretty simple because the state space is very limited. You know that each promise is only going to block in one direction. If you want to block again, you have to create a new promise. And so more logic becomes like data structures as opposed to thinking about hidden implicit states. So I don't know, like it's fairly vague, but if people are interested, later on we can look into how Signal is implemented internally and you have a clear idea.
Ooh,
The
yeah,
big
that'd be
picture
cool.
is the reason we have very simple primitives is that those are implemented as built-ins. So they're implemented in Haskell, implemented in Scheme. So you don't want to have something super complicated as a built-in. You want to have simple built-ins, and then we do more complicated stuff in Unison. So this library is more like slightly higher level than the base one. So you might use ref even in user code where you don't have a map. You want to have some other state. But for example, Signal is very common to want something akin to Signal instead of doing things with promise manually. Signal is a bit less performant because with promise you can be super granular into like what awakens when, whereas Signal is a bit more like every time something changes, awaken anyone that might be interested. But basically that's the relationship. So those ref and promise, very simple built-ins, foundation of everything else. This library a bit more higher level, and you're probably going to find using this simpler than using ref and promise directly at
Gotcha.
first. Then once you get into more advanced stuff, the basic stuff is also not that difficult. It's
Gotcha.
lower level. Yeah.
And just so folks don't get confused, because there's also sort of an async task in the remote or in the distributed
Yeah,
library. So just to disambiguate, what's that compared to some of the
yeah.
stuff you
So
jumped over?
remote as, and again, this is again, if you think, oh, why are there so many layers? It's back to
Yeah.
because of like we're building everything in Unison.
Mm.
So if the cloud wasn't built in Unison, maybe some of these lower layers wouldn't exist. You just use the cloud stuff directly. But because we have to use the lower level stuff to build the cloud, that's why you find it. So actually, remote, you can think of it as like the IO type for the cloud. Um, and so, first of all, if you do want to do some stuff in the cloud, you have to use it. Like that's what we expose. But then it also has some superpowers. It's got multi-machine superpowers, meaning that you can send remote computation across machines and do awaiting across machines. But even when you're doing single machine stuff, it's even higher level. So like remote might take care of like interruption for you, like when you spawn threads in remote and you cancel the main thread, it will cancel the children, and all of this stuff doesn't happen in the lower level layers. So if you want a TLDR for users, I would say start by using remote. Don't worry about IO at all. And you get two benefits. One, your stuff is ready for the cloud, and two, you get all these higher level models for things. Uh, and then slightly lower. If you do need IO for something that isn't cloud based, then this library will help you. And then the final thing I want to add is remote also has ref and promise as the base primitives. So in theory, and actually I need to do it, I just never got to it. We could build a library like this with Signal and Concurrent Map by using remote.ref and remote.promise to build a remote.signal.
Oh,
I just never got to it, but like if you find working with ref and promise less convenient than working with Signal in IO, you're probably gonna think the same with remote. So you have remote.ref, remote.promise. Like, oh, I wish there was a remote.signal. There's no good reason for that not to exist. I need to just write it down. Or someone
that
else can do it and do a contribution.
yeah, perhaps one of our wonderful audience members will take that up. In that
Yeah, and
case, would
if you sorry, if you are an audience member and you want to do it and you want to pair, I'm also off to do that. So
awesome, super
yeah,
cool. In that case, would the signature for like change just interpret into remote instead of IO um,
yes,
as its target? Okay, cool,
that's
cool.
it.
Yeah, maybe someone will pick that up. Um, cool. Well, let's change gears a little bit because I know we've talked about doing just a little bit of live programming to give people a sense of the API of the library, so that
Yes.
they can go off and do their own concurrent programming. So I'll switch screens here. And we had talked about writing a really simple concurrent queue implementation using Signal.
Yes.
So maybe could you talk a little bit about what that would look like? What are some of the use cases we'd want to support?
Uh, I mean, I'm going to assume that most people here have sort of will kind of know why a queue might be useful, which is just a mini recap. You want to decouple work from a producer and a consumer. So you want a queue, and they might be on different threads. They probably are on different threads. So you want to coordinate between them. Uh, and we're going to do something very simple. You can enqueue things in the queue, and making sure that if multiple threads do it, nothing gets lost. Uh, and also you want to dequeue things from the queue. Similar thing, if multiple threads do it, nothing is lost. Uh, and the thing that makes it hard though is like if the queue is empty, we don't want the the listeners to have to like continuously take CPU time until the queue is full. We want them to block until the queue is no longer empty. So that's the thing that Signal is going to help us do.
Mm,
Uh, so that's what we're going to do. That's it. If we have time, we might also put a bound on the queue, meaning we set a maximum size and then writers will also block if the queue gets too big. You see that there's not actually sort of a lot more code, but let's start simple. And the one thing I will say that we will not really think about that much is like interruption. So we're not going to worry too much about what happens if a thread gets interrupted from the outside. That's additional complexity and significant complexity to think about. Uh, So for the sake of simplicity, we'll ignore that. And also remote does a lot of that work for you. So we cannot really showcase that part in IO super well.
gotcha. Okay.
Okay, so to get started, I like to always start by like writing down the signatures for our API. So
Cool.
maybe write I don't know, like an empty queue type, and then what functions we want to write on that. Well, yeah, you're already sort of skipping ahead to what
Oh,
you think is going to be the state, which is,
sorry.
it's interesting. No, you're not incorrect. It's just that someone might not be that.
Right. So I guess the first question to ask would be, what is the sort of data backing of the queue? There's some other primitives in Unison. We could use array, we could use list, which is the one
Yeah,
that I
so for me, that's
gravitate
the
toward.
second question to ask. Like the
Ah,
first question to ask is what are the type signatures that you use to interact with the queue? And then you
okay.
think about representation. Uh,
Okay.
at least that's sort of my style, kind of both valid.
So I think that an enqueue might look like given an A and a queue. We're going to be enqueuing something.
Yeah,
Uh,
so that's actually not the case.
ah,
So that represents an immutable queue. So see how you've returned a new queue. But in a
yes.
concurrent queue, there's not what's going to happen. A concurrent queue, a concurrent anything is based on mutation because multiple threads are accessing it. So instead of being a pure function that returns a new queue, it's going to be a function in IO that returns unit.
Yes. Okay.
Yeah, and
IO is our
yes,
ability here.
yeah, and then yeah, you can just put a to do for now on that.
Yeah. And Q. Man, Q is hard to
Yeah,
spell. Should have picked stack. Um, so DQ is
yeah. By the way, when I'm writing code that isn't public, I'm tempted to just put the capital Q letter to spell these because yeah, it is weird to spell.
it is an annoying word to spell. We'll
Yeah,
do. I'll just work on my spelling. Okay, so for DQing,
yeah,
because I in functional land you give the actual queue that you're DQing. In this
yeah.
case, I still think that's the case.
That's the case. Yes.
Okay, and this one is going to be, and this is going to be in my mind optional in case there's no.
Yeah. So that's also not quite the case because
Mm.
remember, like if there's no elements on the queue, returning optional signals that we want to return immediately with a none. But then what
Ah,
do you do when you have that none if you're already queue? Well, you're gonna spin. Spin just means retrying pointlessly forever. So instead,
right.
it's just gonna return an A. But note that we have the IO ability in there. So the IO is needed because we're gonna block. So the thread is actually gonna block until we have an element. And so you can
Mm.
see like even just the types, there's like some novelty if you just use the like purely functional data structures.
Right, absolutely. So
Yeah,
okay, very cool. So we got NQ and DQ. These are the two core functions of the
yeah.
queue.
And now we also want one to create a queue,
Ah,
uh, which
mm,
again it might be an
empty
interest
or new? Let's see.
up to you. Uh,
Q dot new.
and what's the type of that?
Uh, in my mind, it would just be a Q Q of A
Right. So that's the third
empty.
difference. If it was a queue of A, like a pure value, then every time you create queue, it will be the same queue. So remember here we fundamentally are wrapping mutable states. So creation of mutable state is effectful. So this will not be just a value, but it will be a function from unit to IO of Q. So we have like syntax for this. So it'll be like a thunk in IO. Um, so basically like when we're going to use a queue, you can't just say Queue.new. You have to create it once and then pass it to all the threads. Otherwise, you're going to create different queues. This is, by the way, is a common mistake with this style of like you have a thunk and then you say Queue.new in two threads and then they don't communicate. It's because you created two different ones. You want to
Right.
create one and then sort of pass it around.
Okay.
Okay. Now the good news is like when you implement it, you won't be able to implement new unless it's in IO, so it won't compile. So even if you weren't like able to figure out that this is the case, the type system will not let you get away with it. Okay, so now that we have the signature, we want to move on to the state representation. So
Mm.
you started with some idea, like what was your reasoning for
Uh, so yeah, I had thought a queue, the data backing of it could be a list of A, um, and just
that? Yeah.
use, consing and then get the last element if we wanted to do.
Yeah,
Uh,
so that's correct. The fundamental state of a queue is a list. And by the way, we're using an interesting style of concurrency, which is afforded by this sort of functional languages with effects, like Unison or Haskell or Scala, where we're actually using immutable data, and then we're going to wrap them in mutable references as opposed to having everything mutable. And that actually helps tremendously for the same reason I mentioned before. The state space of possible things that can happen is now smaller. Uh, and I say this to say, okay, the state is a list of A's, but there's not going to be enough to synchronize and modify the state from multiple threads, right? So you modify, you return a new queue, but how do we make sure that the new queue actually goes into the mutable reference? And in fact, there isn't even a mutable reference at the moment in there. So we need some type of mutable reference that contains that list. Uh, and so we could use a ref, uh, and a ref will be enough to do a queue that doesn't block. It will just solve the problem of like enqueuing and dequeuing from the queue in a way that is safe. But then we also need to block. And so, as you might have guessed, there's a data type that might help us do both things with a signal.
Okay. Yeah. So it's
And
a
so,
queue
yeah,
signal of list.
yes, you want parentheses
I
in
do.
there, otherwise it's gonna. Yeah.
Yes.
It's
Uh,
cool. So that's great. So now all the functions. Well, actually, I think we can start from the new function. Uh,
sure.
that's probably easy. Um,
Okay. So we're gonna do queue. So I know signal has a dot new uh, uh,
Function,
constructor.
yeah.
Yeah. Um, so, and let me just double check that in the UCM by opening it before I forget. And I'm going to view it.
Yeah,
And
and
it
see how
looks like.
the constructor is in the IO ability. So
Yeah.
if you hadn't put the IO tank, it will not compile. So you can't mess this up.
Ah, I see. Okay. Okay,
Yeah,
cool. So we're type checking at the moment.
yeah, we're good.
Gotten
We're good. Um, so then both enqueue and dequeue will be using that alter function on signal. Uh, I think it was called alter, or maybe change. I don't remember.
to signal dot change. Yeah.
Yeah, change. Sorry, alter is for the concurrent map.
Okay.
So yeah, we can sort of write a skeleton for both, where uh, we say signal.change, pass it the signal inside the queue. Uh,
Let's do. Okay, so now I've got the signal inside the queue.
yeah,
Um, so signal.change takes the signal.
yeah,
And
yeah.
it takes a thunk of changes.
So yeah, that's the little program. So you can probably put a do in there because it's going to be a block. Uh, uh, yeah,
Okay.
yeah, and then return a unit or maybe to do whatever to make it compile. To
To
do is
do.
like a something that always compiles for in the use case when you're not implementing something right
Okay.
now.
Okay.
Yeah. So we might have to change this structure slightly later on, but it's a sort of starting point that hopefully makes sense. So we have a signal, and signals API lets you write computation over signals. And so this is like the skeleton that we sort of set up. I think you have a type on line 12, an extra D at the end of signal.
Thank you.
Okay, let's start from enqueue. And the reason I want to start from enqueue is because there's no blocking in enqueue at the moment. This is an unbounded queue, so it's a bit easier. We don't have to think about how to express blocking. So based on, if you have a look at the changes ability,
View changes.
yes.
Okay, we've got
How do you
retry, read, and
think,
write.
yes, so how do you think we could write this enqueue function using this ability?
So I know we're going to need to write a new thing to the signal. So we could take our element and cons it to the list, probably by reading it,
Yeah,
um, and then write it. So I guess it would be a read, cons the element, and then write back to the signal.
and that's it. Yeah.
Okay, let's do that. So signal.
So you don't need
Yeah.
to pass the signal because see the
Oh,
changes ability is parameterized by the state. So it's already assuming
oh.
that there is some ambient state that you pass when you call signal.change.
Gotcha. Okay, because it's not like you can have more than one signal, right?
No.
It's just the
Yeah,
one.
the
Okay.
design is that you write computations on one signal and they are atomic. And there's also, by the way, there's also the reason why the type of change does not allow extra effects. So we cannot do IO and stuff from this. This is like, it's very similar to the transaction ability state, except over a single signal rather than multiple pieces of state, like
Gotcha.
transaction.
Gotcha. Okay, so then it's just signal dot write of a plus colon
Yeah, so
list.
you can choose where to append this element. And this is for the audience, but lists in Unison aren't linked lists, so they don't have like a fast cons and a slow on cons. They're both the same. So you can do whatever as long as we don't get mixed up when we then try and read, so that we don't create a stack by accident. Would be
Mm,
cool.
gotcha. Yeah. So we'll have to get from the very end now,
Yes.
given
Yeah.
this. Pro tip: if you are confused about our operators, the colon goes on the side of the collection. So that's how you know
Yes.
which side the list goes on. Okay, cool. So this is enqueue. And signal dot change, does it return unit or does it return something? Just
So
confirm.
let's have a look. If you get, it returns whatever. So the changes thunk is a computation, right? So whatever
Mm,
you return from that computation, it will be what you return from signal.change. This will make sense for when we do a dequeue, where we have to our changes computation will have to return the actual element.
okay.
Uh,
Okay. Cool. Well, let's see if we're
uh,
type checking. Signal dot read.
yeah, this is probably not similar. This changes the read or something.
Ah, thank you. And
And
this
same,
is
same there.
changes.
Yeah.
All right. Okay. Cool.
Okay.
We are type checking.
Okay. Now I'm gonna try to do something that I have to explain later, but it's not too complicated. But basically, instead of inlining that do in the queue, let's write a func with a name, like on line 13 or something.
In line 13,
Yeah, let's try like logic equals do. Uh,
logic equals do. Okay, so we need to extract something into a
yeah,
function.
there's not a crazy. The reason is not like that weird. We need to do some recursion in here, as you will see. So we need that name.
Ah,
Uh,
okay,
uh,
okay.
but yeah, hopefully by the second time you do this, you will know when this needs to happen. But it'll be clear in a second why. So do what to do in that logic, uh, and then we say signal change signal of logic. Now, a tip for people in the audience: don't forget to delete that do on line 17. If you do logic, then you get type error because it's now suspended twice. Okay, so now, how would you go about this DQ logic? Uh,
Hmm. Well, we want it to be blocking,
so
and
let's start from the easiest part, right? So
okay,
blocking is sort of the hardest part. So how do we even start? Because like writing this logic here, right?
okay. So at the very simple, we could read from our changes, and then
Yes.
grab the last element from the list.
Let's try and do that. Yeah.
Okay, let's do list is equal to that, and then do we have a last
I think we do.
function? Let's double check. This returns optional.
Right.
Um,
So what do we do with that optional?
well, if it's none, that's when we would want to recurse, I guess. Just wait until
Well, do
something.
something. We
Yeah,
don't know yet what to do, right? But
yeah,
we know what to do with the song case, though, right?
yeah. We would like to return that.
Right. So let's pass a match. Uh, So that's cool. And now we have like interesting thinking to do.
Mm.
Okay, so what could we do here? We could fail, and that would require, exception in there, but that's not the semantics we want. We could actually return the optional. That's also not the semantics we want. So what else could we do to even make this compile, you reckon?
Mm. What could we do? We could keep calling logic. We could make people give you a default value. We could throw an exception. Yeah, I guess those are
Okay,
the things
so
that I can come
you
up
said
with.
something we could do logic. But by the way, we also need to do something else as well. We have to actually remove from the queue. But let's figure out the blocking. Then the
Yeah,
removal is hopefully pretty easy to put
yeah,
to do that. So if we just retry, right, and by retry I just mean call logic again,
yeah.
what do you think will happen?
If we just call logic again,
Yeah,
it's gonna try and read again.
yeah.
Uh, state may not have changed. It may have changed.
Okay.
Um,
So if it has changed, is it this correct? Correct. I didn't say it like nice. Is it correct?
is it correct in the sense that I want that change, but I may not see
What?
it?
Well, think about. I'm discussing interleavings, right? So I've
Mm,
first submitted an interleaving to you, meaning you find a non that we call logic again. Someone else might have changed it. If he has changed it, is the logic correct? By logic, I mean one where we just call logic again in line 18. Maybe write that down so that it's clear for everyone else.
mm,
Yeah, and remove the to
like
do from that.
if we just did forcing logic again.
Yeah, so we're just retrying, right?
Yeah.
Okay, and now again, trying to think about the possible interleavings. The possible interleaving is the state has changed in the meantime, or the state hasn't changed. So if it has changed, and now there's an element, is this correct? Will it do the right thing?
I'm not calling signal dot change as a block again inside logic. So
That
I
doesn't
don't.
matter though. Single law change is sort of like interpreting this logic to do the low level synchronization for you. But think
Mm,
about this computation. Assume that this it's the mechanics are working, right? Signal law change is
mm.
working. But is this logic gonna work? So you found a none, we retried it, and in this specific case, someone wrote an element to the list. Is this gonna work then?
See, I think it would work, but
So say that. It's fine. It's not I'm not trying to trick you. So
yeah,
So you think it
yeah,
will work? Okay.
yeah.
So let's say, yeah, Paul, you're right. So let's say we hit none instead. So
Mm.
we hit none. We run it again. Nothing has changed. Is this correct?
We hit none again, like a subsequent
Yeah.
time,
Yeah.
and nothing has changed. It would keep calling logic,
Yeah.
and we would just keep going.
Yeah. But eventually, right, it will work.
Yeah.
So it is correct. It's not great because when it's sort of like it's doing what's called like a spin or like a busy wait, meaning we are waiting correctly, but we're doing that by wasting a ton of CPU. We're just doing like that, like empty, 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 empty. So we don't want that, but we kind of wrote the correct logic. Now, the cool thing about Signal is that there's a very easy way of transforming this logic into one that performs the way we want.
Huh. Okay.
Because what we're saying is, okay, if the state is not what I want, I'm going to retry the logic. And the reason that is slow is that we also do the logic if the state hasn't changed. So if the state has changed, everything is good. If the state hasn't changed, we're kind of wasting work. So if only we had a
Got it.
way of like waiting until the state changes, then we could do that before calling logic again, and now it will work. And it's just like, okay, if the state is what I want, cool. If it's not what I want, let me wait until it changes, and then let me try again.
Right.
That's the idea. And if you look at the changes ability, we have an operation, like the third operation, called retry. And what retry does is block your thread until the state of the signal changes.
Mm,
So if we call retry before recurring, we're done.
okay.
So, and the reason I made you write it like this is like first write the busy loop so that you can deal with the correctness, and then just before every recursion, you retry, and that's it.
Right. Yeah, because
That's
my
the recipe.
intuition would just be to do this sort of basic pattern match and recursion coming from sort of a regular functional queue. But
Yeah, I
what you've
mean,
yeah.
the good thing about this is that you will know that this is wrong because the fan of your laptop will start spinning like crazy.
I'll
Uh,
create a space heater.
yeah, you create a space heater pretty quickly.
Okay.
Uh,
Okay. So we need to wrap this call to logic inside change changes dot retry.
so we don't need to wrap it. And maybe we should change the name of this function. We just need to
Mm,
call retry, and it will block the thread. So change the retry is blocking the thread, and it will only return. So you were writing correctly. We just don't need to wrap logic. We just need to do retry before logic.
uh, okay.
That's it.
Gotcha. And so it just looking at the signature of changes dot retry, it returns X, which is sort of like a non-type. Um,
Anything like it will
yeah,
compile
yeah.
whenever you want to.
Gotcha. Ah,
Uh,
okay. That's pretty cool.
yeah, Mark
Uh,
points out that you're missing the changes. Um,
thank you.
yeah, that's correct.
Changes.
Now we do have a bug, uh, but just because we forgot to do something,
Uh,
we forgot to
we
actually
need to
like, yeah,
update this first before we return it.
yeah.
Okay, so let's
Also, I
see.
think maybe it's a bit easier to
Not that.
pattern match on the list directly as opposed to getting lost and then having to call init.
Okay. Pattern match on the list with. Let's see. So I need the end one. So
Yes,
that is something plus. Or can I do this? That? A?
you can do that, but you don't want the, yeah,
That? Yeah.
yeah,
That is my case where I have something, and this is changes dot write
yeah,
the prefix,
yeah.
and then otherwise,
Well, but then you want to return the thing, right? You want to actually
oh,
dequeue it.
and A, and then otherwise, that is this
Oh, by the way,
case.
let me give you another piece of advice for concurrent codes.
Mm.
Avoid these like catch-all things. You want to think about your state pretty carefully. So the more you use like catch-all
Oh, like the
cases, the
underscore
more,
thing.
yeah, the more it will make it hard for you to deep. Not in this case because we have a list, but if the state is complicated, I actually prefer to write down everything and then say bug, this cannot happen. And then if it does happen, you'll see, oh, this is the thing that actually happened, even though it wasn't supposed to, versus underscore and something that is different from what you expect happens. And now it's hard to know, you know why.
Gotcha. Okay,
Uh,
so that's a pro tip when writing kind of concurrent algorithms is don't be too loose with your
yeah,
catch-alls because it catches too much.
yeah, it's a bit less, a bit uglier and more defensive, but it will work. So in this case, we don't have to. We can just write empty list, and we don't have to have any explicit calls to bug or anything. We just
Okay.
yeah, we
Yeah,
just
let's
use
do
the empty
that.
list.
Empty
By the way,
list.
bug, if you haven't heard of it, is like just a way of signaling that the code is not going to happen. If it does happen, it's going to crash. Uh, so it's like sys.error, basically, if you're used to languages that have that. Um,
Okay.
yeah,
Yeah,
and
should we try and
that's,
run it?
yeah, let's do that. How would you do that?
Let's write a main function. Main. Okay, so I'd like to create a queue.
Yeah.
Queue equals Queue.new. Okay. And I could enqueue some stuff.
So that's you can do that, but it's not interesting because it's
Mm.
happening sequentially.
Oh,
So we're not
right.
testing
Okay,
like
we do it in a fork. Have one fork that like writes a bunch of stuff repeatedly, and then
yeah,
have like another fork thread rather that is reading stuff.
yeah. So what I like to do for these is write little funcs for workers and for maybe for a worker and a reader, so that we can do little loops.
Okay, maybe producer.
Yeah, or producer and consumer is another good name. Yeah. Um,
Okay. Um.
and then for the producer, what we might do is maybe write a few numbers with a with a recursive function. Uh, or with range, but what I want to do is actually wait some time in between them, and
Oh.
also yeah, print line I'm printing, so you kind of when you run it, you'll see the order in which things are happening.
Okay. I always get the order for each wrong.
I
All
think
right.
you're
There's this one. It's
that's
this one.
correct. Yeah.
Okay. It's the one with the underscore at the end. Okay. So cases I. Oops. NQ and
No, Mark. Line 17 and 20 don't need a do. Do is not a marker, a syntactic marker for like a scope. Do create a function from unit to something. So do suspends execution is like this. So in that case, we're not trying to create extra thumbs. We just want to do. So it's not replaceable for braces. Indentation is a replacement for braces. For braces, do just creates thumbs. Cool.
okay, and I
Yeah,
guess
if you want to do something even nicer, well, let's start. Like I like to do some randomness on the sleeping, so that you actually do see more interesting interleaving stuff. Uh,
okay. Yeah, we could do. See, is there like a random nat in?
yeah.
Yeah, let's do sleep time equals random.nat in, and let's say you are 10,000 microseconds to.
Yeah, but we have a sleep that takes a duration if you don't want to deal with like multiplication of microseconds.
Indeed,
Uh,
I don't want to do that. I
yeah. So I
okay.
think if you
Let's
call,
do
yeah, so you can do say that these are, yeah, let's say between 100 and 300 milliseconds.
100 and 300. Yeah, that's a good
Yeah, and
range.
maybe let's make them like 10 numbers rather than 100. We don't want to be waiting here for 3 minutes for this one. In that range closed.
Uh,
On line 35.
online 35.
Yeah,
10? Just to 10.
like 10 or 15, something like that. We don't want to wait too
Yeah,
long.
let's do 15. Okay, cool.
Uh,
And we
and
want it
let's maybe sleep before we enqueue, so
sleep
that we kind
before.
of know which is what. Because if you enqueue before we sleep, we might get print lines that are a bit wonky. But you know, it's
Gotcha.
sort of equivalent. To be honest, it's not incorrect. It's just
Okay. Okay, so sleep dot. Is it sleep dot duration?
I think it's just sleep instead of sleep microseconds.
Ah, gotcha.
Yeah.
Duration dot.
I think there's a millisecond help or something. Yeah.
Yeah, cool.
So then let's print line something. Yeah,
It's not show, it's to text.
yeah. And that's our producer. Uh,
Oh, that's right. All right. Is there
yeah.
an
So this is one of
int?
the things that we like. Remote is a bit nicer at dealing with durations for
Yeah,
very
you could have a
historical
negative
reasons.
duration.
Yeah.
Duration, millisecond sleep time. Let's see. Was there not an int in?
We can just do 9 and convert to int later, I think.
Okay, let's do that. Okay, second argument to enqueue has type unit to
Yeah,
queue. Oh, I need to force this
yeah,
to be an actual queue. Okay, cool.
cool.
That's fine.
Yeah, and now let's try the. That's not going to do what you want. We're just going to force it. We want to fork it.
Oh,
But maybe let's try the consumer first.
okay.
Uh,
Okay, so I feel like for the consumer, we should read
yeah,
from the queue. Um,
yeah.
so we need to do that in a signal.change. We can't just call read.
No, we can because if you see the queue is already we already
Uh,
wrote a function. Yeah,
right. Okay, so dequeue queue.
yeah,
All right, this is a
yeah.
okay. And should this have any sleeps to?
No, let's just print. Let's
Okay,
just print. It will tell us when when it has received it.
cool.
And then you want to recur that. If you do this, it will just read one. Yeah. And also we want to do the same. Oh no, producer, we don't want to do that because we're doing a range.
Yeah. Okay.
Cool.
So now we want to do these in forks, separate threads.
Yes, so there's a bit of a thing with fork. Again, it's due to the fact of how low level the IO building blocks are. So fork does not accept exception,
Right.
but some of these functions return exceptions. There
Right.
is a nice way of solving this problem, but let's do it the not so nice way
Unsafe
because we're gonna have a
run.
lot of time. Yeah, let's do unsafe run. So you wanna
Okay.
do
I
you
can
wanna
just
first of
can I
all
wrap
do
all of it?
yeah if you want yeah. Uh, by the way, the
Um.
nice way would be to like create a function that creates a promise and puts all the errors that can happen in the thread in that promise, and then we can read the errors later. Whereas what we're doing now with that unsafe run, we're basically discarding the exceptions into the void. So don't actually do it because if you have a bug with this, the exception will not be will be swallowed, and you'll have a really hard time to know what's going
Gotcha. All right, and this one
on. And
also needs unsafe run.
because of the print line, yes.
Yeah. Yeah. Okay.
Uh,
And we want to do unsafe run do.
yeah, and again, the ones in remote don't have this weirdness. So
Gotcha.
yeah, let's fork the consumer first, although it doesn't really matter. Uh,
Okay. You fork.
yeah,
All right, and it does take a delayed thing here, and it
yeah,
returns a thread ID. Okay.
yeah. Let's ignore the thread ID with underscore equal. The thread ID might be useful for interruption, which we don't want to talk about today.
Okay.
And let's also fork the producer. By the way, the reason I forked the consumer first, and I'm also told you to wait before you enqueue, is so that we have a higher likelihood of seeing some blocking happening.
Ah.
And in fact, let's maybe add uh, a single print line to both blocks saying producer starting and consumer starting. So we will see.
Gotcha.
And by the way, this is another tip, like sort of uh, trick of like writing down these print lines. And then when you want to convert these to tests, instead of writing print line, you write these strings to a ref, and then you have like an execution trace what has happened. so we kind of know what we are, uh, you know, what we're dealing with.
Okay, I'm just pulling this into a loop so we can do the, because we only want to see the consumer starting one time, right?
We do, yeah.
Okay.
You need to force a loop at the end of this function again.
Again. Oh,
So you wrote loop as a function, but you haven't actually. Uh,
so this needs to be do
yeah,
unsafe run, do print line, blah, and I'm forcing loop here
yeah, but now you want to call it.
at the very end. Yes.
Yeah, yeah.
Cool. Cool. Oh, we need some random. We need random.
Uh, that is not gonna work. You let's see. This is another thing that remote solves. Uh,
Yeah.
let's do it this way. Do a split mix in here. Uh,
After the unsafe run, or
it doesn't matter.
enclosed by it. Random dot split mix.
Yeah, I think there is. So just, yeah, let's maybe do that.
Huh.
And let's. There's definitely
I
the other random nat. You can use that to see the split mix. Uh, yeah, I
okay.
don't know. Maybe either in the office hours or another time. I'll talk about these little trick guns. Again, this is stuff that if you write things in remote, you're not dealing with. Uh,
Uh,
but in this case, you have to know a few of these details, which are annoying. But if you can just call the random nat as the second argument of split mix. We don't want to use it
gotcha.
directly because you do want to have a range. Otherwise, we'll end up waiting. They want to do that, not a let.
Okay. It's not a let. It takes a delayed computation.
Yeah.
Okay.
So split mix is a handler for randomness, and then random nat is going to seed it with the random nat. Uh,
Okay.
and this is cool. We just want to just put a unit at the end. This is what it's complaining about. There we go.
Ooh. Okay. Should we run
Yeah.
it? Let's do it.
Yeah. Let's see. Let's hope we get some nice bugs.
Oh. Oh. Uh-oh. Did I forget to force something? Because that looks to me like did not did not run something. Um, double check. That returns forced view. Let's say run. That also forces the execution. Oh no, these are supposed to be.
Yeah.
So I don't see any of the print lines. Which is a bit odd. Is something being swallowed? I think
Yeah.
the
Yeah.
main thread
No.
just exited.
Yeah, yeah, yeah.
Yeah.
So this is what's happening. I was gonna see how would you have tried to debug it? Because this is exactly the type of thing that you might encounter in the wild. And then,
Right.
uh, yeah.
Ah.
So I'm gonna try to show you the what you shouldn't do, but we will
Okay.
do it for now. What you shouldn't do is try and use sleeping to fix this problem. And the reason sleeping doesn't work is that it's gonna be super non-deterministic. Let's start from that just
Okay.
to see that that's the problem. But then forking it properly might requires promises. Uh,
Right. Okay.
and see
So
if
we
that's the
could
problem.
do sleep duration dot seconds 10
Yeah,
plus 10 positive seconds. Ah.
yeah. So that's it.
Okay.
So it is that. Uh,
Yeah.
okay.
Consumer
So
producer enqueued one, dequeued one.
yeah.
Yep. Okay. Very cool.
Uh, I want to close on a happy note. So I'll show you the proper way.
Ooh,
although it's
yes.
maybe requires a bit more explanation to make sense. But what we want to do is um, let's do it super simple. Let's create two. What's the simplest one? Okay, so in this case, we know that the consumer is all, well, the reason I said it, if you think about it, we kind of wrote something infinite, right? If you look at our consumer, it never stops. So we don't have a decent way of thinking, oh, you know, when to stop this.
Mm.
Um, so, we could just say this runs for 10 seconds, which is what this thing is doing. Or we could say, oh, the consumer stops once it has queued a certain number of elements. And then if we do that, we also could say that the main thread stops when the consumer stops.
Ah,
So
okay.
do you think we have enough time for that? I think it's going to be like 5, 10 minutes.
Yeah, I think we have enough time.
Okay. So let's start the logic that makes the consumer stop after a certain number of elements dequeued. So let's add a nat in the function. We can just use or maybe it's just in the loop actually.
Oh, in the loop
Uh,
itself? Okay.
yeah, yeah,
Okay. Let's do bound. Or limit. Yeah,
yeah.
that's a better word. Limit. Okay.
And then we can just say in line 49, not there, but like in line 49, we can just say, uh, if uh, limit equals whatever. Let's say uh, let's say 8. Just random.
Okay.
How many are we in queuing? Let's say 8. Let's say 10. We're in queuing 15.
Okay. So
Uh, then just return unit. We stop recurring. If not, we
else
loop.
loop. Need parens. Limit. Increment limit.
Yeah,
Okay, and then this gets called with 0.
yeah. You don't need the exclamation mark.
Ah, you're right. Now that this
Yeah,
has
you
an
don't.
argument, we don't need this to be a delayed
Yeah.
thing. Perfect. Okay.
You also put a bunch of Lispy parentheses that don't really need. UCM will
Okay.
remove them for you later, so it's fine.
Yeah, you can have bad style, and the UCM will help you.
Um, cool. So we have done that.
Cool.
And now, this is a bit less intuitive as to why this sort of needs to happen, but pass an argument to consumer, which we'll call uh, stop,
Stop.
and that argument is going to be a promise. So let's create a promise right
Ooh.
before a line 43. Let's do
Okay.
stop equals, uh,
Stop promise.
well, I don't like Hungarian notation, but it's,
Okay. We'll do stop is equal to promise dot new.
yeah, I think it requires a forcing. I remember if it's not new or empty, but new. Nice.
New. It does require
Yeah.
forcing.
And
Okay.
and
Oh,
what
do
we're
we
gonna
need to
do,
complete the promise in our end condition?
that's it.
Ah. Okay. So it's not just if limit equals blah, then unit. It's you have to write something to the promise. Is
Yeah.
it
So there's a promise
promise
dot
dot?
write. Yeah, use the write underscore, which discards the promise returns a boolean to tell you if it's the first time you write it or not. We don't care. So just use
Uh,
the yeah.
right. So if the limit is equal to that, then write the promise.
We need to write something to it, which in this case is unit. We're creating a promise of unit. Promise of unit, by the way, add a different order for arguments.
Oh, it doesn't take the unit
Yeah,
first.
yeah, takes it
Okay.
last. Uh, this is of when you have a promise of units, you might have the name gate or latch for it in other languages. Um,
Gotcha.
and now, instead of doing that sleep, let's do a read on that promise. So a promise.read will block when the promise is empty. So what we're doing, we fork these two threads, and now we're blocked on the promise. Eventually, the consumer runs, and it will unblock the producer runs, and eventually will enqueue enough things to the consumer. The consumer will stop, it will complete the promise, and then the main thread will advance. And then in the Haskell implementation, the main thread will then cancel everything. Uh, and sort of this makes us do all these bits.
Okay. And promise.read.
Oh, you have to pass the promise. Oh, you know what? We don't actually have to have it as an argument. We created it in advance. Let's just close over it. So
Okay.
we'll just stop at line 47.
Yeah. Got it.
And also, I
Okay.
think oh, cool. Let's try that.
Run. Main.
And there we go. Well,
Amazing.
it only took us like 2 or 3 minutes extra time. So good. Yeah.
Perfect. Okay, cool. Well, this has been so fun. Thank you so much, Fabio, for sharing your wisdom and for teaching us all
See,
about.
now,
Yeah, this is not
now,
that scary, folks, right? I
now
expect to
you're a
see.
practitioner. So we also got a nice bug. You know,
Yeah.
you're a pro. Uh,
Oh, Alvaro has a question. Why the call to bang logic? Da, 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 da. Intuition says that's dead code. Okay, where is that?
It's not that code because so let me just can we take a 7 second break because I think my laptop is about to die.
Okay,
Uh,
1 second. Think of
try
your questions.
explaining it, Rebecca, and
What?
see.
Oh, God. Okay. Well, shit. Uh, this called the logic here on line 22. Oh, we've got multiple voices in the chat being like, why is it needed? I'm kind of curious what happens if we comment it out. Shit doesn't break. I did not expect that. So Chris says, if retry returns any, how could it possibly execute anything past it?
So I think the probable answer is that I started with this style that actually required you to do recursion yourself, and probably I changed it to behave like Alvaro specs, and I just don't remember because I haven't used this library in a while. And so it might be that just do a retry, and it's even simpler. Uh, but I did want you to learn about the recursion because that's what's happening actually under the hood. So I do think that you just need to retry, and that would be fine.
Okay, so y'all are on some galaxy brain thinking here,
Yeah,
because you don't actually need
yeah.
logic anymore, because retry is listening for
Retry
the
is actually
change.
retrying for you. Yeah, yeah.
Mm,
Yeah, so I think it's like now that memories are coming back. So I started the API with, a wait for changes, and then you would like call wait for changes, and then you'd have to retry manually. But then people that don't know about this pattern wouldn't know that that's how you need to use it.
yeah, so logic
Uh,
was an artifact of our building
yeah,
towards this ultimate implementation. We just
yeah,
had like an
yeah,
extra thing.
yeah, yeah. So if you
Ah,
actually look at how single dot changes implemented, it's
mm.
actually using a promise to wait for changes and then doing the retry recursion for you. So it's still useful information for people to know. Actually, look at that case now at the very bottom of everything,
Promise read, waiting for change,
and
and
then
then
that
press
changes
change.
it's the recursion. Yeah,
Uh, oh, that's
yeah,
cool. Oh, that's
yeah.
very
See,
cool.
changes is doing recursion on the whole thing.
This is awesome. We've got a lot of great conversation happening in the chat. So I think with this, we'll head over to probably office hours for folks who want to hang out, chat, talk about concurrency, hang out. But again, thank you so much, Fabio, for doing this and for telling us about this concurrency library. And I hope folks feel confident in going about and making use of it. And we'll see lots of cool additional libraries built atop of it. So thanks so much for joining, folks. Bye.